when we get to 3C matrices, this is quite similar to the review part of this lecture that we've done in the beginning of the semester. So let's say that if you have, say, a T, a linear map from V to W, so that there's a, with basis 1 for V as V1 through Vn, and basis 2 as W1 through Wm, so that V is an n-dimensional vector space and W is an m-dimensional vector space. In such a case, if we have T of V1 represented as, say, A11 W1 plus A21 W2, and then so on, A M1 Wm, and you do that for the next guy. So this will be A12 W1, A22 W2, A M2 Wm, and then until you reach the very final, which is TVn equals A times 1n W1, A 2n W2, A mn Wm. Yeah, so let's say this happens. Now, writing down such a system of equations is always possible because T is a linear map from V to W. So since V1 through Vn's are vectors in V, of course, TV1, TV2 until Tvn, all of these will be a vector in W. And since W1 through Wm is a basis for W, this can always be represented as some linear combinations of basis 2, W1 through Wm. And I'm just calling these coefficients in some manner, some pattern, okay? Now it will turn out that I will always name it in this way, where the, if you write it in this way, the first number will be increasing order for each of the lines, and then as you go down, it's the second number that becomes higher. Okay, so this is going to be our convention for the naming of the coefficients. And going back, you can always come up with such an equation for any linear map from T, V to W with some chosen basis for B1 and B2. Okay, so in such a case, very early in the semester, I explained that you can write down the matrix of this linear map going from B1 to B2 as A11, but somehow these now get written downwards. Okay, so the next guy that gets written over here is not A12, but this is A21, all the way down to AM1. And the next one is A12, A22, and then all the way down to AM2, until you hit A1n, A2n, all the way down to AMN. Okay? So that's how I explained, and sometimes you do want to remember that this is the matrix which uses B1 as the basis for the domain vector space, and then B2 as the basis for the target vector space. So that's what we did earlier in the semester, okay? Now in the book, they use a different notation, which is this same thing is now called matrix of T going from B1 to B2. Okay, so the content of this 3C is basically just redoing everything that we did in the review part, because there's nothing different. Now what does get a little confusing is that in our previous notation I wrote down B1 over here and wrote down the arrow this way, going opposite, right? B1 goes here and then B2. The reason I do this is because if you have, so let me write it in some other color, I don't want you to write this down. Or if you want to write this down, write it in some corner, okay? So I'm trying to say that if T is a linear map from V to W, and then S is a linear map from W to U, and let's say you're choosing basis B1 for V and then B2 for W, so that you use the same basis for W, but then you have B3. Okay. Now, let's see if you understand this notation. Which one's defined? TS or ST? Which one's the one that's defined? Is TS the one that's defined or ST that's defined?
ST3.
It's ST because if you take something in V, T of V goes into W, and anything that's, this belongs to W. Anything that's in W can now be sent to U by doing this. Whereas this doesn't match because the target of S is U, and that's not in the domain of T, so this doesn't make any sense. Okay. Now, so if you understood that, now you can say, well, if you have a matrix representation from B1 to B2, and then matrix representation of S from B2 to B3, then with the arrows going backwards, then this kind of makes sense, because you can say that, let me delete this. So you can say that if you take T, T, okay. If you take S, B2 to B3, B2, going this way, and T going from B1 to B2, then the matrix multiplication, the resulting matrix multiplication, will be same as computing the matrix for the composition of two linear maps going from B1 to B3. See, B1 is the basis for V, and B3 is the basis for U, and clearly this composition gives you a function, gives you a linear map from V to U, right? So this notation makes sense easily if you put the arrow this way. Now, this is not the standard convention. A lot of the other books would rather have it the other way, which is B1 to B2 and B2 to B3. And you can kind of see the confusion here, right? This results in B1 to B3, and if you put the arrows this way, you can't do the same thing where it's like you have to do B1, B2, and then you have to go here and take B2 to B3. Whereas if you change the arrow backwards, that way, then you can just read this and you say, oh, B1 is sent to B2 and B2 is sent to B3, so of course the resulting will give you B1 sent to B3, right? So having the arrow this way has a clear advantage when you compose things, and that's why I have the arrow this way. So right now, I guess only a small percentage of the textbooks adopt this notation. Others will have the arrow the other way. Some even have no arrows, but they might have something like S with B1 to B2, so like going up. Yeah, so there are so many different notations that people have adapted, and this is yet another notation. Yeah, and I like this the best. I mean, even although the textbook, Axler's textbook is excellent, this is the standard textbook for pretty much many of the math departments that are notable in this country. So it's a very famous textbook. So there's some excellent things in that textbook, but I don't like the choice of the ordering. But if you're writing it this way, I guess writing this as B2, B1 kind of doesn't make sense. You don't have an arrow. At least here you have an arrow to say that it's really B1 to B2. If you put B2, B1 without the arrow, then there will be another major confusion. So I guess the author didn't have any choice but to write it this way. Yeah, but I just want you to be aware of the fact that when you compose, the order might be a little different than the way you read. So hopefully you're not going to be confused with that. All right. And this part is called a matrix, and I mean, we're assuming that everyone still remembers the previous calculation-based linear algebra, so hopefully you know what a matrix is, and this first number gives you the row number, so they all have one, so this top row, that's called the first row, and you can see that the row number is 1, okay? And now it's the row number 2. The second number is called the column number, and you can see that if you select all the members with the second number 2, you get a column. That's the second column, right? So that's how we read the matrices, and such a convention of using the first number for the row and the second number for the column is pretty much universal. I can't think of a single textbook that has it the opposite way. So yeah, I don't think anyone would do that thing. So just treat this as the universal format for writing a matrix. Always the row number comes first and then the column number comes next. And if you think of these vectors as if they are column vectors, then the matrix multiplication, the way that T operates on V is like the matrix multiplication of this times the column vector representation for V1. So see, V1, the coordinate matrix for V1 under B1 is, well, who can tell me that? Yeah. What's the coordinate matrix for V1 with respect to B1?
1, 0, 0, 0.
Yes, because V1 itself is the first guy, right? So you can think of V1 as 1 times V1 plus 0 times V2 all the way to 0 times Vn. So the coordinate matrix is like 1, 0, 0. Like that, okay? And indeed, if you take this viewpoint, then this times this matrix times this matrix will only pick up this column, right? And that column is really the coordinate matrix for this vector here. Okay, yeah, so that's why the numbers go down. These numbers they go down that way. So hopefully that's yeah, that's another point where things do get confusing. Like why aren't we writing it down exactly like that? Why are we like it's more like a transpose. You know what a transpose is, right? Something that's a row becomes a column, something that's a column becomes a row. So it's as if you took all the coefficients, made a matrix, and you transposed it to get the matrix of a operator. And if you think of these vectors, you replace them with their coordinate matrix as column vectors, then it kind of makes sense why it becomes transposed. All right. So let's do an example. We've done tons of examples before, but let's try one. So, example. Let's say t of x, y, z given as 3x minus y plus z, and then x plus 2z. So in the second one, there's no y there. And we're going to view t as a linear map from R3 to R2. It makes sense because you're feeding in 3 numbers, so the domain is 3 numbers, so it's vector space of R3. And then the result is something comma something, so it's 2 real numbers, so the result is the vector space R2. Okay, now furthermore, let's assume that the first basis, the basis for R3 is 1, 0, 0, 1, negative 1, 0, and then 1, 1, negative 1. Okay? And then let's also assume that the basis for B2 is, well, let's just use 1, negative 1, and then 0, 1 for B2. Okay. And the question is, find matrix representation of T and from B1 to B2. Okay, let's try to solve this question. Solution. Okay, so this prescription says you have to apply the linear map to each element of the basis, get something, and then once you get that something, you have to represent them as linear combination of the target basis. So let's do exactly that. What should I plug in first? T of
1, 0, 0.
1, 0, 0, that's the first guy, right? So you do 1, 0, 0. And therefore, this is going to be 3 times 1 minus 0 plus 0, 1 plus 2 times 0. And that's equal to 3 comma 1. Yeah, these are all zeros, that's 0. So the only thing that's non-zero is 3 times 1 in the first coordinate and 1 in the second coordinate. Okay, now we have to rewrite this as, so now we need to rewrite 3 comma 1 as something times, so let me use the same notation as there. So A11 times W1, which is this guy, plus A21 times the second guy, which is 0, 1. Okay, let's try to find what these numbers are. So 3 comma 1 is equal to, well, it's just A11 times 1 and then comma. The second one is negative A11 plus A21. Sorry, this is like the big comma. There are small commas here. Hopefully that's not going to confuse us. All right, so that immediately tells us what? A11 is 3, right? Because they have to be equal coordinate-wise. So this must be 3. And now you have this as minus 3 plus A21 equals to 1. So 1 is equal to minus 3 plus A21. What does that mean? A21 is? 4. Okay, good. So I know that this, the very first guy, is 3 times W1 and 4 times W2. Okay? All right, so let's continue on. We have T of, the next guy is 1, negative 1, 0. So that's going to be 3 times 1 minus negative 1 plus 0. And then 1 plus 2 times 0, which is 4 comma 1. Okay. And that has to be equal to A12 1, 0, no, 1, negative 1, plus A22 0, 1, so that you have 4, 1 equals to A12, comma, negative A12 plus A22. That tells us that A12 is 4, the first coordinate should match, and then 1 is equal to negative 4 plus A22, so that A22 is 5. Okay. Lastly, we have to apply T to 1, 1, negative 1, which is 3 times 1 minus 1 plus negative 1, and then 1 plus 2 times negative 1, so that it's going to be 3 minus 2, which is 1, and then 1 minus 2 is negative 1. Again, I need to write that as A13, 1, negative 1, plus A23, 0, 1, and here we've done enough math, enough calculations that's similar, so we can say A13 should be 1, and then negative 1 is equal to negative 1 plus A23, so that A23 is 0. Okay, so with all that, what's our answer? Well, remember, all these numbers should be written as columns, so the answer would be that the matrix representation of T with B1 to B2 is going to be the matrix where you put 3 and 4 as columns, and then 4 and 5 as the next column, and then 1 and 0 as the last column. And that's it. That's the matrix representation of T. Okay. And this is exactly what we did in the beginning of the semester, just new notation, that's all. So if, maybe I should say note, if the basis for V and W are obvious. So, e.g., if you have like 1, 0 and then 0, 1 for R2. So if you have R2, then the first easiest basis you can think of is 1, 0, 0, 1, right? So in that case, we just write matrix of T. Okay. Or if you just want to say it in general that for any B1 and B2, you just, if you don't need to say it explicitly, we can just hide it. Okay? So in some cases, you write it like this because there's some obvious choice of the basis. In some cases, it should really be written as MT B1, B2 in general, but you just don't write it. Okay? So those are the two cases. And with those two conventions, with this convention, we have some obvious theorems. So there's the 3.36, which says that the matrix of the sum of two linear maps is same as matrix of S plus matrix of T. Yeah, we learned what S plus T was for two linear maps, right? Last time. This is kind of very straightforward, but let me try to write down the proof anyway. So here, let's say S and T are both a linear map from V to W with some basis B1 through Vn, and B2 W1 through Wm. And then we're just going to suppress these when we write down M. So there's this, it's suppressed, but these all mean B1 to B2, B1 to B2, B1 to B2. Those are just not written. And then in such a case, then you can say that S of V1 is equal to A11 W1 da 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 A M1 Wm, and then S of Vn is A1n W1 da 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 A Mn Wn. Okay. And in the same way, you would do T of V1 equals to A. Oh, this time, it could be the same number, but most likely usually it's different, so I'm just going to use B. Okay. So there should be some constant B11 times W1, and then Bm1 Wm, all the way down Tvn B1n W1 Bmn Wm. Okay. Now, if this is true, then you know what SVK plus S plus T of VK is. Okay, so by definition, the map S plus T, the sum of the linear maps, take any vector in V as S applied to VK plus T applied to VK. Okay. But what is SVK? Well, that's same as summation of A, JK, WJ, okay, then plus summation B, JK, VK, WJ, sorry, WJ. So you can put them together. You can put these together as summation of A, JK plus B, JK, WK. Sorry, hopefully the sudden appearance of the summation doesn't throw you off, but sigma just means it's a shorthand for writing dot dot dot, right? So don't be too surprised. What I'm trying to say is that because the second number is same as this number, S of VK would mean A1KW1 dot 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 all the way to AMKWM, and this second number K doesn't change for the entire summation. That's why this this summation is really under J, okay? So if K is fixed, okay, K is a fixed number, and then you're adding for J from 1 through M. Yeah, so I might even write 1 through M if you want to. But rather than trying to make that explicit, you just have to think that it's some dot 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 notation that I'm trying to write, okay? But if you think of those dot 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 notation, and then you can combine like terms, and you can end up with this. So I wrote it like this, but in my mind, what's really happening is like I'm really thinking of A1K plus B1K W1 plus da 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 AMK plus BMK WM. That's what's in my mind. Even if I'm writing this, this is what I'm really writing. Okay. If that's what you get is, then that tells you that the matrix representation of S plus T is what? It's A11 plus B11 as the first guy, right? Is one number. Right? And the next guy will be A12 plus B12 as the second guy, and all the way up till AN1 plus BN. Sorry, what's happening? Oh, sorry. B1N plus B1N. A1N plus B1N as a single number. Then goes down here, that's AM1 plus BM1. And then this will be AMN and BMN. Just like that. And that is indeed the sum of AIJKs, right? AIJ plus sum of BIJ. And individually, this one is the matrix of S, and this one's the matrix of T. Okay, so, and then here I'm assuming that you already know how to add matrices. So I'm assuming that you've taken the calculus-based, calculation-based linear algebra before, so you know how to add matrices. So under that convention, this makes sense, okay? And then in 3.38, there's another identity which says m of lambda t. So you can multiply a scalar to any linear map, and that's same as lambda times the matrix of t, where here I'm assuming that you know how to multiply a number to a matrix. You know how to multiply a matrix, right? If you have a matrix and you multiply 3, that means you multiply to every one of these elements, right? 3, 6, 9, 12. So assuming that you know this, then you get this identity as well. And if you put 3.36 and 3.38 together, then you see that this M is a linear map, right? So this is homogeneity, and this is additivity, right? So what 3.36 and 3.38 is showing is that 3.36 and 3.38 is saying that M takes any linear map from V to W to the space of matrices. So let's see, M N. So this is spaces of matrices with M rows and N columns. Remember, the first number is always the row number. Second number is the column number. So this gives you the space of all matrices of M rows and N columns. Okay. So there's this M is a map from any linear map to its matrix, and this 3.36 and 3.3 is showing that this M is a linear map between these two. Okay. And see, we also learned that if you have the space of linear maps, last time we showed that this is a vector space, right? And this one is just like if you have like lots of real numbers with commas or in some format, it's a vector space, right? So this is also a vector space of dimension. What's the dimension of Fmn? What do you think? M times n, right? So if you have, for example, if you have a space of 2 by 3 matrices, what's that? 2 rows and 3 columns. So this will be an element in F2, 3, right? And you have 6 numbers, right? So that has dimension 6. Okay, so this has dimension Mn. And this M is a linear map between 2 vector spaces. That's what's being shown, okay? And then we're going to add some notes later on in the next subsection that this is actually it's a bijective map. It's both injective and surjective. And if that's established, you can say that this is an isomorphism between 2 vector spaces. So this is a way to say that this space and this space, they're both vector spaces, and they're isomorphic as vector spaces. That's what I'm trying to say here. Okay, so 3.41, it's just revisiting the matrix multiplication that all of you already know. So let's think about this. If you have A1, A2, A3, A4 times B1, B2, B3, B4, what's the result? It'll cross down, right? So it's A1, B1, A plus A2, B3, across down this is A1, B2 plus A2, B4, across down that's A3 times B1, and A4 times B3, and A3 times B2, A4 times B4. So it's just revisiting this multiplication. However, why are we multiplying matrices in such a strange way? Like, for example, we could define matrix multiplication as this time this is like A1, B1, A2, B2, A3, A4, A3, B3, A4, B4. Why don't we multiply matrices like that? Why are we doing that? Have you ever thought about that? Why matrices are multiplied that way? By the way, this is sometimes called dummy product or Hadamard product. This has a notation. It's like something like this. It's a element-wise multiplication, and this is sometimes used, not as much as this other one, but it does get used. So nobody thought about why? Well, when these things called matrices were first invented, they were invented to study linear maps. And because of that, it was made so that the matrix multiplication is compatible to multiplication of linear maps. But multiplication of linear maps is a composition of linear maps, right? So let's think about that, okay? So let's think about all of these on the standard basis, the I and j for R2, okay? And let's say this is the matrix for T, and this is the matrix for S. Let's think about that, okay? All right, so T of 1, 0 equals to something times 1, 0 plus something times 0, 1. Okay, tell me what that is.
1, 0.
No, T of 1, 0. What is T of 1, 0? I said we were thinking of this as if it's a matrix times a column vector, right? What do you get if you do this?
A1.
A1 and then
A3.
A3, right? So that's what we get. So what do I put here and there?
A1, A3.
A1 and A3, right? Okay. And likewise, if I do T of 0, 1, what do we get?
A2, A4.
A2 plus A4. Okay. So that's that. Now, tell me what T of xy is in terms of something comma something.
A1 plus A2.
No, it's A1x
Sorry, A1.
plus,
A3.
is it A3y or A2y? Which one?
A2. Oh, wait, no. A2x. Or,
It's A2y, but
or A2y.
okay. Let's think of this way. What is xy? This is x times 1, 0 plus y times 0, 1. Isn't that right? Okay. And because T is a linear map, it has additivity and also homogeneity, so you end up with x times T1, 0 plus y times T0, 1. Isn't that right? Okay, now what is T1, 0? We have it here, right? So that tells us we get, let's see, what do we get? We get A1x 1, 0 plus A3x 0, 1. That's just for this. Okay, I just multiply x to here and there. Okay, and then this one will give you A2y 1, 0 plus A4y 0, 1. Okay, now put them together. What do you get in the first coordinate?
A1, 1, 0.
A1x plus
A2y.
A2y, and then
A3x.
A3x plus A4y. Is that good? All right. So in the same way, what is S of xy?
B1x plus B2y, comma, B3.
No, it's not A1. Oh, B1 you say?
Yeah,
Okay,
B1.
yeah. B1x plus B2y, B3x plus B4y. Okay, now, see, I want this times this to be the matrix of TS. So let's compute TS of xy. Okay? Let's compute TS of xy. First, remember this is what? This is a composition of functions, right? So you should really think of this as T of S of xy, right? And what is that Sxy? We have it right here, right? So T of B1x plus B2y, B3x plus B4y. Okay? And yet, we still need to plug this into T, but it's a bit confusing because I have Txy as this formula. So this is our this is a formula for x and y, but instead of x we have this complicated stuff. Instead of y, we have this complicated stuff. So we have to be really careful. So let me use a different color so that we don't get confused. So this is like our x, this is our like our y. So when you write that, a1 times x plus a2 times y, comma, a3 times x, and then a4 times y, like that, I shouldn't be using x, but rather, instead of x, I have this guy, right? So I should really be writing b1x plus b2y. And instead of y, I should be using b3x plus b4y. And instead of x, I should be writing b1x plus b2y. Plus, finally, this one, b3x plus b4y. Okay? Now let's expand and organize in terms of x and y. So if I multiply them out and gather this one with this one, here's what we get. We get a1b1 plus a2b3 times x plus. Okay, help me out here. What goes here?
1b2.
A1b2 plus
A2b4.
yeah, a2 times b4. Okay, again, we want to multiply out and gather the one with the x. I see the a3b1 is multiplied, and over here a4 and b3 are multiplied. And for the y, a3 times b2, and then a4 times b4. Okay, now do you recognize the formulas here? This is exactly this guy, right? This is exactly this one. This is this. This is this. Okay? So that's why the matrix multiplication is written in such a weird way. Okay? If you ever wondered why people multiply matrices this way, it's done so that this is true. So the natural outcome of this discussion is that I'm not going to prove this, but this is going to be true. Okay, that's 3.43. Okay? 3.43 says that if you have the matrix of T and matrix of S, you multiply them, you get the matrix of the composition of the two. Okay, some more notations. You have 3.47, which says AC JK equals to AJ dot C dot K. All right. To explain what's going on here, let me first say that matrix A is this one, A11. Sometimes I put commas in between, but if it's obvious, I'll just write A11. This doesn't mean it's A11, but it's A1, comma 1, okay? So what's here? What's the next number? 1, 2, or 2, 1?
1, 2.
1, 2, good. All the way up till A1N. And then here is A M1, A Mn. Okay, so that's going to be our A. Now, for AC to be defined, what dimension must C have? So A is what by what? This is what by what matrix? How many rows?
And done.
M rows and N columns, right? So this is a M by N matrix, right? Now for A times C to be defined, C must be N by some K, right? So C must be N by K. So C has to have C11 all the way up down to CN1, and then it has to be C1K and CNK. So this has to be N by K matrix, and only when the inner dimensions match, you can multiply the two, and the result is this one is a M by K matrix. That's what you get. Okay, so that's what you learned before. Now let's talk about AJ dot. So what does this AJ dot mean? So what does A1 dot mean? A1 dot means it's everything that has 1 in the first number, but the second number can change from all the possible numbers. Okay, so it starts from A11 way up to A1N. See, 1 is fixed, so this is going to be a row matrix. Okay, so in this matrix, the very first row is called A1 dot, and therefore AJ dot means it's the jth row. Is that okay? It's the jth row. On the other hand, if you have dot comma K, then of course the K, which is a column number, the column number is fixed, therefore this will be a column vector. Okay? And several times you probably heard that when you multiply matrices, you have to do across down, right? So you have to do a multiplication between a row matrix from the first guy and a column matrix from the second guy. And then if you take the jth row and kth column, and this is really a dot product between them. In other words, you do component-wise multiplication and you add the result. So it's a dot product between these two matrices. And that result becomes the jth row, kth column element in the resulting matrix. So this will be an M by K matrix whose j comma kth element is given by the product of a row from the first matrix and a column from the second matrix. That's what this formula is saying. Is that okay? Right. So that's what 3.47 is saying. Okay. So 3.49 has this idea. If you have the product matrix, so let's say AC, we'll just denote this as B, okay? So that you have B11, and let's see, this is M by K matrix, so it goes up to K, and then B M1 all the way till BMK. So that's what AC is, okay? And if I look at the kth column, so I'm using K here, sorry. Let me write a different number for this one. I'll put L. Okay. So if I look at the Lth column, so here's L, which starts from B 1L all the way up till BML. That's same as A11 all the way up till A1N, AM1 all the way till AMN, times C is C11, C1K, CN1, CNK. And there's a way to see where this came from. This thing is same as just taking the entire thing multiplied by the Lth column, which is C1L through CNL. Okay. So if you do this times this, we already know that if I have a matrix times a column vector, you end up with another column vector, right? Where this length is same as the row number of rows here. So the number of rows of this matrix is m, and therefore you're going to get a length m column vector, right? And this part is exactly same as this times this. Okay? So that's what this formula is saying. I'm just teaching you how to read these cryptic formulas. And once you understand their meaning, then the next time you see it, it should make sense. Okay? Right. And then finally, there's another cryptic formula which says in 3.52, if you have A times a column with C1 through Cn, that's same as C1 times A, the first column, plus C2 times A, the second column, C, Cn times A, nth column. Okay, that's what you have. And you probably have seen this before, like say you have 1, 2, 3, 4, and you multiply 10 and 100. This result is same thing as multiplying 10 to the first column vector and multiplying 100 to the second column vector, which is 2, 4. You can check that. You can check the left side and the right side, and you'll see that they're exactly the same. Okay. This times this, what's that? That's 210, right? That also gives you 210. This times this gives you 30, and then 430. So that's exactly 430, right? So 3.52 is just reiterating that if you multiply a matrix with a column vector, that's like taking linear combinations of the columns of A. That's what it's saying. Okay? Such a way to view matrix multiplication is handy when you do the diagonalization, which we actually implicitly did when I was reviewing the diagonalization for 2 by 2. But later on, we'll do diagonalization of 3 by 3 and more complicated.